is in there.
So I already see one question. I can just start with that.
Okay.
So it says, to obtain latency and energy consumption optimization, is it worth sacrificing some accuracy? And will slight accuracy loss affect the task significantly? That is a great question. I think it really depends on your particular application and also the platform that you're doing. So for example, if you are doing, let's say like voice recognition or kind of speech recognition on your phone, for example, you have very limited amount of compute there. So there, in order to be able to run on your phone, it might be okay to sacrifice a little bit of accuracy so that you even have the capability on your phone or on these like IoT devices. Just to even make it possible, you're going to have to significantly reduce the energy or the latency to get that to become accurate. However, those, and these are typically, like I said, like a voice wake up, for example, like when to actually wake up. And so and in those applications, it might be okay to be, slightly off a little bit. But then there's also, of course, applications like you want to think about the medical space, for instance, where you really don't want to sacrifice accuracy as much as possible. Or even, so then there's like the interesting area of self-driving cars, right? Where clearly accuracy is important because you don't want to have an accident. But at the same time, latency is also very critical because if you don't get it to run as fast as possible, you also can't react to your surroundings. So you have to be careful with the trade-off there. And often with self-driving cars, what they do is they also complement it with some other algorithms that are running in parallel to give it some redundancy. So it really is very much application dependent. So there's no secret recipe like, oh, I'm willing to trade off 2% accuracy, 1% accuracy. It really depends on your application. As an engineer and as a computer scientist, what you want to do is try and provide the best optimal trade-off that you can achieve, right? Engineering versus accuracy. But which design point to pick is really application dependent.
Okay, thank you. Any other questions?
I got another question directly sent to me that was asked.
Okay, go ahead.
Yes. Which platform is best for embedded implementation of DNNs? FPGAs, embedded microcontrollers, embedded GPUs, and I would also say specialized hardware. So there's obviously going to be different trade-offs in terms of these platforms, in terms of how energy efficient they might be, how fast they might be, but also how flexible they might be and what are the costs associated with them and how hard they are to use, right? So for instance, when you have embedded microcontrollers and embedded GPUs, they're often, the software stack for them is often pretty easy to use. They're pretty flexible. The cost of them can be quite low. So that's certainly beneficial. But in terms of the types of optimizations that you can do underneath, from a hardware perspective, it might be quite limited, right? You're limited to whatever hardware they already what functions they can already support, right? So for example, if you have very sparse compute, for example, we talked about sparsity there, GPUs have more difficulties exploiting that, right? So they can't necessarily translate that to efficiency. Whereas with things like FPGAs and specialized hardware, you can actually, go down and really optimize much more for your given workload. Now, of course, the challenge for these types of platforms is that the design process is going to be much more challenging, right? So if you want to use an FPGA, especially if you want to write specialized architectures to exploit these properties of your workload, is going to take a lot more time. Similar to ASICs or specialized hardware, that's going to be even more costly to do, but the energy and the latency benefits you would get from really specialized ASICs are also going to be much better than FPGAs, and what you get from FPGAs potentially could be much better than what you might get on an embedded GPU or a microcontroller. So it's really a matter of how well the workload aligns with the underlying architecture. If they align very well, so for example, GPUs do matrix multiplications very efficiently. So if you could just do everything as matrix multiplication and you don't want to exploit sparsity, then maybe GPUs are a good fit. But if there's some properties in the workload that are not a good fit for GPU and you want more specialization, then moving to FPGAs and then maybe down to specialized hardware will give you much better improvement, but it's going to be at a cost of longer design time and just the cost of the platform itself, especially specialized hardware.
Do you see any other questions in your chat? stack?
Yes,
No?
I guess people are sending it to me privately. Okay, so there's
Okay.
another question. I have seen binarized neural networks which decrease accuracy but simplify the weights. Could you share your feelings for BNNs, binary neural networks? Is it a promising neural network? I think for some applications, it certainly is quite promising because again, these type of really, really embedded IoT, we were trying to run a microcontroller. Your only option really is in some of these to run I shouldn't say only option, but like one of the things that they do run are binary neural nets. I think some people are trying to explore non-binary neural nets for these type of platforms, but so they're a good fit for that. But yes, certainly they're going to sacrifice accuracy. So I think the one thing is a popular approach that people might take is more a kind of a tiered approach. So you might have an always on super low power neural network running just to like filter the it's always listening, and then when it's classifies something as interesting, then you have like the next tier that then turns on a much more like higher powered neural network but also much more accurate neural net, right? So you kind of use the first stage as a filtering mechanism for the second stage and then so on. So this is a very typical thing that you might see in an actual system where you might put binary nets at the very beginning where, it can run all the time because it's super efficient, but if it misses, if it passes things that might not be super relevant, it's still okay. It's not catastrophic. So you really have to think about what the application is. But I think that's one promising use case of binary neural nets, kind of always on, kind of wake up type of systems. Okay, another question was, given the AI accelerators, oh, do we have time for that or should I drop?
No, go ahead, because I saw that something showed and then I don't see it on my list. So there was another question for you.
AI accelerators have been intensively studied for several years with great achievements. Is there still major insignificance? Still major insignificance for these hardware accelerators? What does that mean? Is there still like opportunities to be done in these hardware accelerators? If that's the case, I certainly think there are. I think, and hopefully from the talk, some of that was conveyed. Like certainly there's been a lot of focus on, for example, increasing tops per watts and so on. But at the end of the day, you want to do high energy efficiency, and low latency, right? And I think that those remain challenges, particularly because of the diversity of the neural networks that are out there. So having flexible hardware that can support a wide range of neural networks is really important. I think the other aspect that we talked a bit about here also is sparsity. So in fact, in our book that we've written, we spent like a whole chapter going through the sparsity and how to support that, because we think that that's a really critical area moving forward. First, where are the sources of sparsity that you can find in the neural network? And then how can you design hardware to efficiently exploit that? How should you think about the process of designing hardware to do that, right? So what are the key concepts or principles from a hardware design perspective to supporting sparse computation? So I think that there's a lot of exciting work in that space. There's certainly also on the training side of things, I didn't talk too much about it in my talk, but that's also an increasingly important area of research.
I have a question. So you talked about memory stores. How to bringing computation to memory? Obviously, that's a very important thing. But how mature is a memory store technology now so that we could use it or start using it?
Yeah, I think that's a great question. I think some of the foundries already have some, memristor types of processes that you can use. I think a great place to look at research in that space is probably ISSCC and IADM. These are conferences where you see routinely papers being published of fabricated chips using memristors, for instance, to perform computation for deep neural nets. I think one of the challenges that you often see, though, in these spaces is that they're still quite small in terms of the types of neural nets that they can support, right? So I think one of the challenges that they're facing is, can you scale? What does it mean when you scale up this technology? Also, what does it mean when you build a full system around this technology as well, right? So I think, the technology is somewhat good, and I think it's like enough that you can prototype and build systems, but I haven't necessarily seen, products of it, though there are interesting startups that are looking, at least there's like, for example, there's a startup called Mythic that's looking at, from a flash-based memory point of view, can you build accelerators based on that? And I'm sure there's other startups looking at memristor-based systems as well.
Are they by nature analog, or they can be done done sort of in the digital domain?
I guess it depends on what you mean by on a digital day. So like traditionally, what they're all trying to do, as we mentioned, was to exploit the conductance of those devices,
Right,
and then use, Ohm's law and KCL to do the multiply
right.
and accumulate.
But you can also think of them as being connected or not connected, and people are trying to actually implement logic gates even with memristors, in which case it's not as simple as the combination logic, because it requires several steps to go through it. That's what I understand, at least, and that will
Right.
be difficult. So I think thinking of them as being really analog makes a big advantage, because you can simply, as you said, using Ohm's law, you basically add them together, and you in fact implement multiply and accumulate by doing this, right?
Correct. Yeah. Yeah, so I mean, you can certainly think of it as like if you just treat each memristor as still binary on and off, for
Right,
example,
right, right,
and then
right.
you need to like outside the loop accumulate, across the different
Okay,
bit lines, the values. You can certainly do that. I think one thing that you lose is obviously density,
sure.
right? That's going to be a problem there. And then also, yeah, you lose a little bit of the parallelism and stuff that you got. So you have to say at the end of the day, then, was it worth doing it this way versus another way, right? So there's certainly, I think that's another thing that we do talk a lot about in our book, and actually like excerpts of our book that are on the IRIS website, you can also, I think,
Right.
discuss this in terms of just what are the challenges in this space, what are the different trade-offs. It's really nice, like we talked about, to think about from the Ohm's law point of view, the benefits of this, Ohm's law and KCL, but
Right.
when you start scaling up, there's a lot of trade-offs that you need to make, right? And so
We probably have time for one more question, considering that we started a little late. And can you see anything on your stack here on your chat?
nope, I don't see
No.
anything.
Then I have a quick question, if I may. So in one of the energy aware pruning methods you mentioned, as a suggestion, was to prune, for example, layers that assume the most energy first. But wouldn't that sacrifice in accuracy and adversely affect accuracy? I know that's just an idea, but there's more to it than just
Yeah,
cutting off something that consumes most, because that may actually provide most accuracy, right?
of course. I think what we're talking about is a way to jointly consider
Right.
accuracy and energy. So, of course, as I mentioned, like one of the reasons why people are super excited about neural nets is because of its accuracy. So you don't want to sacrifice too much of that, like we just
That's
talked
right.
about from an applications point of view. But the question is, if there's many ways to achieve that accuracy, can we pick the path that requires the least amount of energy? And so it's kind of a joint optimization of the accuracy and the energy together. And so one of the reasons for energy aware pruning, where we prune the layers that consume most energy first, is not because we're gonna we just like want to blindly prune them. We're asking, like, in this layer, if we remove energies and weights in this layer, each of these weights are likely to consume more energy, and we remove it to a point where the accuracy has not dropped too much, because we know that the more you remove, the more likely the accuracy is going to drop. So how can I find the weights that I can remove that save me the most energy without sacrificing too much?
Right. Very good. Well, thank you very much for this excellent talk and the great answers.
Thanks for the great.
Well, unfortunately, we don't have a way of clapping and thanking you in person. Thank you.
Right.
So that concludes our session, keynote and welcome and opening remarks session. And what we'll need to do now, we'll probably take a few minutes of time to switch between the rooms. I would like to remind you that those of you who want to go to session 1A, novel architectures, will stay in the same Zoom ID. Those of you who want to go to session 1B, you will have to leave this room and go into the second room, which is, well, Zoom 2. You should follow the instructions, okay?